Okay, there is 2 homework assignments. They're both due on Friday, but if you need more time, let me know, because as long as we redo the due date before that passes, I can add more time. Otherwise, you'll get all of the answers, and then there's kind of not a point to doing the homework if it just tells you what the answer is. But if just 1 or 2 people want an extension, I'll just change the date for those people, and then the rest of the class will turn in the homework, on Friday the 11th. It was a welcome back quiz and everyone got full credit. I had to make it graded so that I could write responses to you, but I just gave everyone full points. If you haven't done the quiz, do it soon and I can give you feedback. I told the class that you need to understand how to do problems 3 and 4. If you want other examples for those problems, like come visit office hour. Tomorrow is my first in-person office hour, so after class I'll go over to Shasta and I'll kind of give you more information about that tomorrow. Right. I shared an announcement about the math lab, which is in Brighton 118. So you can get help on those problems if you don't want to visit or if you can't visit office hour. And they can help you with your homework, which I'm going to try today to write to you guys. I'm sorry that I haven't written back to your questions, but I'm catching up. And I'm going to help you with an instantaneous velocity problem after we kind of check out those. We asked about trig functions that have an input of pi over x. I posted a picture of it. We're going to look at the picture, do a practice problem, and then do notes for chapter 2.4. Okay. Let's look at that picture that I posted. So this is on Canvas in week 3. I just need a minute. Okay. So I'm going to zoom in. I think that we talked about cosine of pi over x. And we graphed values of x that are greater than 0. And the function comes down, goes up, and bounces up and down, but never actually reaches x equal to 0. On the other side, go down, come up, bounce along over and over again.
Okay, what does that e equal again? I forgot.
Exists in, yeah.
Okay.
So on the domain is all x that exist in the real numbers are. or real numbers.
But
Such
they
that-
don't equal 0.
Yeah, does not equal 0. All right, and then I grabbed a picture of sine of pi over x. So it's similar, but this one comes down and up and bounces along. The other side, it kind of goes up, then down, and then bounces along. But it's a domain of all x that exist in the real numbers such that x does not equal 0. And then this last one here, which of course there's a ton of functions out there to look at, but I picked tan of pi over x. And you've got these tangent functions going along closer and closer to x equal to 0, but does not reach that value. The same thing happens on the other side, gets closer and closer. Lines, 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 closer and closer together. Well, curves, I guess, curves. And the domain is all x that exists in the real numbers such that, this part's a little weird, the 1 over x plus 1/2 does not exist in the integers, and this is the important part, x does not equal 0. So these curves get closer and closer to x equals 0, but never actually reaches that part. Okay, so those are a few interesting trig functions, which, by the way, there are infinitely many messy functions out there, but we're going to look at nice functions that are easy to graph. All right. Now I'm going to do a problem that should help you with your homework, but if you need more help with your homework, again, visit the math lab, visit my office hour. I really want to start the notes for 2.4 today, which again, I won't test you on 2.4 material, but is definitely an important part of understanding what's happening in calc in this class. Okay, we have a ball that is thrown into the air and its height in feet after t seconds is given by y equals 40t minus 16t squared. Find the average velocity for the time period beginning at t equals 2 and lasting the following times. So I set up a table to keep things organized. And on the first column, it's the values for H. Next column is where you start. Then we have a place to end. And at the last column is average velocity. Okay, so the first time period is 0.1 seconds. We start when the time is equal to 2 seconds. So end when you are at 2.1 seconds. Get your average velocity, scratch work. All of these are going to start when t equals 2. Okay. It's a slope where you put in f of 2.1, subtract f of 2, divide by 2.1 minus 2. Put this in the calculator and got negative 25.6. Here we're going to do 0.05 seconds of time that's going to elapse. So time interval goes from 2 to 2.05. You get your average velocity just like this. That time went through the calculator and gave me a number of negative 24.8. H. H is the amount of time that has elapsed. Let me double check that really fast. Yeah, it's a period of time. So where is the what's the average velocity after 0.1 seconds, starting at, yeah, so the amount of time that's elapsing is getting smaller and smaller and smaller. And then we're finding the average velocities as that happens. Or you could do it like the difference between 2.1 and 2 is that 0. Is that 0.1. The amount of time that goes between here and here is there. The amount of time between 2 and 2.01 is 0.01.
Professor? Oh, sorry. So what's the difference of the average velocity and the instantaneous velocity?
The average velocity is like the velocities as that time gets smaller and smaller. And then the instantaneous velocity is the slope of the tangent line right at h equals 0. So
So for the average velocity, you would just do like the problem how you have it on the board, right? And then for the instantaneous velocity, don't you like you would like multiply whatever number they give you like on the problem?
actually, you want to come over to the table and guess from those averages what those numbers approach. So like it's getting closer and closer to the average velocities get closer and closer to the instantaneous velocity.
Oh, okay.
Whatever number this is getting closer to. I'll draw a picture once we do this last one.
Okay.
Okay. So this time you're putting in 2.01 and then divide by 2.01. Okay. I got it. Negative 24.16. We'll do part 2 and then I'll try to draw a little pretend graph and talk about the picture, like how to see what's happening.
Is B gonna be instantaneous velocity? Awesome.
Yeah. I think it says like estimate. So I was going to try to use notation, but it was getting a little messy and I like ran out of time. So I'm just going to put down my estimate. So my average velocities get closer and closer to the instantaneous velocity. I've got a negative 25.6, negative 25.8. Hang on, let me check this number. This is, oh yeah, it is smaller. It's negative 24.8 and then negative 24.16. So that decimal got smaller. And what do you think we're getting closer to? Anybody? Huh? Negative 24. You get your values of h smaller and smaller, like put in a 0.0001 and then do that average velocity, you get closer to negative 24. It keeps on.
Yeah, see, I think the problem is that when we try doing it on, the homework, I think like there's like a specific answer for that. So like if we could just guess it and it'd still be wrong. I think that you did like an equation in the book. If you could do that, can you show us like the equation way of finding the instantaneous velocity?
I'll think about that. I think I need to look at your homework.
With the
Yeah.
homework,
I think I know what you're talking about.
with the homework, there was actually more requirements. There wasn't just 3 levels. There was like 5 or 6. So it was approaching something like, let's say 24.2 something something. So if you entered 24.2, it would be the acceptable answer, only because there was a larger variety of numbers approaching it. So you could see us getting closer and closer to that point.
Okay. Well, again, I'm gonna check your homework questions after class. That's my goal. If you put in a guess that's like, also, oh, there's another thing too. And sometimes you need to read the problem and say like, it'll ask you to round a certain way. Anyway, I'm trying to say, if you put in a number and it's pretty much the right answer, I can override the score and give you points. So you don't have to keep on doing work to get that answer that the online homework wants. As long as I know that you've gotten the right guess, I can give you credit. So if you're having an issue with getting the correct answer, getting a check mark, but you've got the right idea, I'll check on that. Just write to me. We can save you time and energy. I'm going to finish this question, but I'm going to save more homework problems for another time because I really want to do some notes today. Last part about this guess is that the slopes we found in the numerator, it was a difference in feet. The denominator was a difference in time in seconds. So your units are feet per seconds. So yeah, if you did a problem and you guessed something like negative 24, but it wants negative 24.02, I'll just fix that for you. I'll give you credit because you're getting closer to this number. It doesn't have to be so precise. Okay. Any particular homework problems that you want me to talk about in the future or any concerns about the class? Let me know tomorrow. I can bring examples for our next meeting, but right now I want to go back to notes for 2.4. So we'll get back to doing homework when we meet together. Oh yeah, I wanted to draw a picture of what you can think of is happening. It's not probably the exact function that we had. I'm going to draw some kind of random function and draw the average velocities and then like what your instantaneous velocity is, things like So again, this isn't the function from the problem, it's some random function. Just going to draw x's, y's, start here, curve over, call this f.
Are we still on B?
Just like an idea of like the whole problem, the whole process.
Okay.
We answered B, this was negative 24 feet per second. Okay, so the instantaneous velocity should be the slope of the tangent line right at that specific time. So what is the slope of the line that touches the curve right at 2, whatever that height is? Okay, we had 0.1 seconds go by. So we're looking at 2 over to 2.1. I'm exaggerating a little bit, just having it a little further from 2 than this number would be, than that number. So say it's 2 to 2.1. Over here to this line. And then we got the slope of the secant line that went between the points 2, f of 2, and 2.1, f of 2.1. Got the slope of this line. All right, and then we went from 2 to 2.05. Which is a bit closer to 2 than that number was. Then we found the slope of the secant line from 2, f of 2, and through 2.05 to f of 2.05. We've gone from like a slope like this to this, and then we're going to do another slope this way. It's the slope of the secant line through 2 f of 2 and the point 2 f of 2.01. Which is even closer to 2 than those other numbers were. So over here, go at the point on the curve, draw a line through that point and the other. And as the elapsed time gets smaller and smaller and smaller, these slopes get closer and closer and closer to the slope of the tangent line right at the time t equals 2. Because it's pt. Okay, and so you're getting these slopes getting closer and closer to the slope of the secant line, which is that instantaneous velocity. I'm going to bring back what that definition is. Read it out again. So I have in my notes Instantaneous velocity is the instantaneous rate of change in a moving object's position. And your average velocities are your change in position divided by change in time. And then I wrote that the limit as h goes to 0 of your average velocities is going to be your instantaneous velocity. Okay, I hope that helped. Of course, your homework will help. I'll get to answering those questions today. Let's work on chapter 2.4. I started with the picture, and then we're going to get into the definition. We're going to come back to 2.3, but I'd like to talk about what it means to find these limits. And these are going to involve proofs, which you would do if you're on a math journey. Eventually you'll get to doing proofs, and you'll do things like this all the time. But in this class, it's not something I would test you on. It's just for understanding and practice. I'm going to draw a quick sketch of curve, and there's going to be a hole at the point where there's no point at AL. Over some number A, have x equal to A right here. And then y equals L. And then our function came up and over, so the spot missing, and it keeps on going. Call the function f. Write what it means to have the limit as x approaches a of f of x equal to L. All right, here's the definition. And this is something that when I run into other math people, we all kind of know this one, memorized it, but don't worry about that right now. It's something I want you to have at least seen before. All right, for all epsilon greater than 0. This symbol is epsilon. Oh,
What's epsilon?
yeah, I'm actually going to back up. Epsilon's just a symbol. It's a Greek letter. I forgot to introduce a few things. I'm sorry. We want to talk about our function and a little bit of extra stuff, and then we're going to write down that epsilon part. Okay, we want to have f be a function defined on an interval around x equal to a. Okay. This function is defined on an open interval around x equal to a. So like this, our function is defined right here on an interval around x equal to a, an open interval. So it's curved bracket. Curved bracket.
I've never actually tried it.
Right. And it doesn't have to be defined right at a, just around x equal to a. Then the limit as x approaches a of f of x equal to L means it means that given epsilon greater than 0, let's scoot that down. Epsilon, it's a Greek letter. So some kind of is a symbol for some number greater than 0. I'll draw a picture in a bit. There exists a delta greater than 0.
So epsilon just means any number, right?
Yep.
Any number, does not like delta, right?
Just like delta, delta is also some number greater than 0.
Okay.
A picture is going to help, but we want to get through what we need to say. Scoot that down. That's another Greek letter. It's delta. You've got some number delta greater than 0. Right? Given epsilon greater than 0, there exists a delta greater than 0, such that if the difference between x and a is less than delta, then the difference between f of x and L is going to be less than epsilon. So this is-
Just a quick refresher, delta also means any number, right?
yeah. Usually you pick kind of a small number, but it's some real number. Okay. And this, so that's your delta, your some number. And then this here is the absolute value of the difference between x and a, which means the distance between x and a. And then we have that less than delta. Try to draw better. I don't know if it's supposed to touch or not touch. It's just a symbol. Okay. When the difference between x and a is less than delta, then we'll have the difference between f of x and L being less than epsilon. These are absolute value bars. We can take the absolute value of the difference between two numbers. That's going to be the distance between those two numbers. So in my notes, I wrote it, I labeled this, but I'm just going to talk about it. So this is telling you that it's the distance from x to a. And this part, the absolute value of f of x minus L, is the distance from f of x over to L. Okay. Add a little bit more to what these pieces mean, and then we're going to go back to, I think, our graph. Yeah, then we're going to draw a picture. All right, before we erase anything, let's read this one more time. So again, I I can run into someone, like I ran into someone in an art class who had taken calc before. And then I turned to him and I'm like, hey, do you know this one? Given epsilon. And he's like, yeah, epsilon greater than 0. There's a delta greater than 0, such that if the difference between x and a is less than delta, then the difference between f of x and l is less than epsilon. I'm gonna laugh and then go back to drawing. Okay, so this piece here, you'll have a negative delta less than x minus a less than delta. And for that part right there, you have a negative epsilon less than f of x minus l less than epsilon. I'm going to work with this part a little bit. Oh, sorry, as an f of x. Okay, we're here. I'm going to add an L to all 3 of these pieces. Have plus L plus L plus L. So L minus epsilon would be less than f of x. And then that would be less than L plus epsilon. Oh no, we're out of time. Let me make sure. It's 11:20, so we're gonna call it good for today. And then when I see you tomorrow, we can talk about homework if we want to, but then we want to draw a picture of what's going on here. So I'm gonna read it out one more time and then say goodbye. The definition of the limit as x goes to a of f of x equal to L means that given some epsilon greater than 0, there will exist a delta greater than 0, such that if the difference between x and a is less than delta, then the difference between f of x and L will be less than epsilon. All right, I will see you tomorrow.